In this lesson we're going to look at the electrolysis of an ionic compound in its molten state. Now remember that in its solid state it consists of positive and negative ions held together by strong ionic forces in an ionic lattice. Okay, and this ionic substance could be, for example, a salt or typically a metal oxide. And because the ions are held by these strong forces, they're unable to move, and so in the solid state the ionic compound cannot conduct electricity. Now to be able to do that, it's got to be changed into an electrolyte, and in this case we're going to do that by heating the compound and making it melt. Okay, so the ionic compound is in its molten state. We have the molten electrolyte rather than an aqueous electrolyte, which we'll look at in the next lesson. Now we also use the word fused. We say that the compound is in its fused state. So you've got positive ions called the cations, and we have the negative ions called the anions, and they are free to move and conduct electricity in this molten fused state. So we have the negative terminal and the positive terminal, and so this electrode is negative and this electrode is positive. Now the positive cations will be attracted towards this electrode, so this is the cathode, while the negative anions will be attracted to the positive electrode, so this will be the anode. So let's have a look and see what happens at each of these electrodes. So first of all, the cation, which we'll represent with a generic M, right, for metal, and that's got a positive charge. So at the cathode, what's going to happen is the cation is going to gain an electron. We represent that with this half equation. So it gains an electron and becomes an atom. So we say the cation gains an electron, and another way of saying that is that the cation is reduced. So an ion is reduced when it gains an electron. In other words, on this electrode, reduction is taking place, and this is called the half equation. Now for example, if the charge on our metal were 2 plus, for example, then we would write the half equation like this. You'd have M2 plus, and this time it would pick up 2 electrons. It would gain 2 electrons before it forms the atom. Now let's just have a look and see what happens at the anode. Now just for the sake of argument, let's just suppose that our anion, in this case chlorine, okay, let's just say it's Cl minus. Well, at the anode what will happen is it will lose an electron. So we represent that like this. We say that the Cl minus becomes Cl plus E minus, and you say, well, chlorine doesn't exist like that in the atmosphere, so we've got to put a 2 there because it is a diatomic molecule. So you're going to get the gas chlorine liberated here at this anode. That's going to be Cl2, but that means we need to balance this half equation. So we've got a 2 there, we're going to need to put a 2 there. But now when we're balancing half equations, we also need to balance the charge as well. So because we put a 2 here, we've now got 2 minuses there, so we need to put a 2 there so that the equation, the half equation, is balanced. So we say that at the anode, the anion, in this case chlorine, loses an electron, and we say that the anion is oxidized. So oxidation occurs when the ion loses an electron. Reduction occurs when the ion gains an electron. And we say that at the anode, oxidation is taking place. In this particular case, our gas is being liberated at the anode, and well, at the cathode, clearly what's forming is the metal. So the metal will start to be deposited on the cathode.